Our second is going to introduce you to finding derivatives.
There was square one. There was
And we're going to look at rates of change. First of all, there's an average rate of change, which you use all the time, right? If I was driving from here to Brandon, which is about 200 kilometers away, and it took me 2 hours, then on average, I was driving 100 kilometers per hour, which technically means I was probably speeding at some time. Because I don't think you can just set the cruise at 100 and go through a whole bunch of those little towns without slowing down. If you do, that would be probably a little bit problematic. So that's an average rate of change. So we have the following graph, and we can calculate average rates of change from 1 on this domain, from 1 to 3. From 1, you start at 6, you go up to 12. So your change in y is 12, your change in x is 2. And if you take your change in y over your change in x, you'll get an average of 3 over that unit, which is exactly the same as the slope of that line. The slope of that line is 3 from 1 to 3. From 1 to 4, this is going to be sad, okay? This is like, if this was distance traveled, you started at your house, it was at 1-6, you went to your friend's house, then you came back home. Once you get back home, your change in y is 0. And your average, therefore, would be 0. This is personally why I have a tough time, like, going for a run for exercise. Because if I'm going to go for a run for exercise, I leave the front of my house, I run around, and where do I get back to when I'm done? The front of my house. And I'm like, mathematically, I could have got here a lot quicker if I wouldn't have left. Right? So I have a tough time doing that kind of exercise because I'm like, well, I'm already back at the front of my house. So why should I get tired and sore and all of those other things? And from 1 to 5, now our change in y is going down 6, so we write a negative 6 there, over 4, negative 3 over 2. Your slope of a line is your change in your y over your change in your x. So finding the slope of a line is like finding an average rate of change. So even if you have a different kind of curve, you could still find the average by finding the slope of a line through any 2 points. And a line that goes through 2 points of a graph is called a secant line, which gets us to our definitions in the next little part. We have a secant line, a line that goes through a curve, usually at 2 points. If you pick any 2 points on a graph and join them, that makes a secant line. Then we have a tangent line. A tangent line is a line that touches the curve at 1 point and usually doesn't cut through the curve. So in grade 9, you did circles, and you had tangents on the circle touching the circle at only 1 point. You may have skipped that unit. I don't know. But if you remember tangents from grade 9 math, they were touching a circle only at 1 point. Secants would cut through, take any 2 points on the circle and cut through them. That would make a secant line. Usually a tangent line doesn't cut through the curve. We'll look at some special ones that do. And then there's a normal line. For those of you taking physics, you've done this a little bit. You've got a tangent line, and then the normal line is perpendicular to the tangent line. So if you find the slope of the secant, that's your average rate of change. If you find the slope of your tangent, that's an instantaneous rate of change. So my driving to Brandon, my average speed was 100 kilometers per hour because it took me 2 hours to drive 200 kilometers. But if you would say, hey, you're on the highway right now, what does your speedometer say? I'd be like, ooh, right now it says 120 kilometers per hour. That's my instantaneous rate of change. I was speeding at that point. But it's 110 on there, so that's not too bad, right? Isn't the speed limit on the Trans-Canada 110? So 120 wasn't too bad. If it was like 180, then it'd be like, oh, this is not good. So what we're going to find out is how these things, the slope of the secant and the slope of the tangent, are related to each other. Now first we'll do this graph right here. This is your distance from Winnipeg. Oh, this is not good. Somehow you got 200 kilometers away from Winnipeg in 1 hour. I hope you were on a plane. Okay? So, if we can calculate the average rate of change between 0 and 1, that's 2, which technically is 200 kilometers per hour if we used units. From 1 to 3, your change in x is 2, your change in y is going down, so you get negative 1 over 2, which would be negative 100 over 2 kilometers per hour. What does it mean if you're going negative 50 kilometers per hour? Well, it just means that you've got a direction now, right? You were getting farther away from Winnipeg, and now you have a speed that's getting you back closer to Winnipeg again. So in each of these, if we want to find the average rate of change, we find your change in y. So from 3 to 4, you're going up 1 in your y value. And from 3 to 4, you're going up 1 in your x value. So this change of rate would be 1. The slope would be 1. From 1 to 4, your change in y is nothing. So your average speed would be 0. Right? If I think to last week when I was teaching you guys, and all that I've moved and driven and everything, my average speed from last week to now is probably close to 0. Because maybe last week I was standing here. And I would move this distance over 5 days. That's not very fast. So my average speed would be close to 0 over the last 5 days. And the last one, see if you got it right. Also a change of 0. So all we're doing is, to find average rate of change, is connecting two dots and finding the slope of that line. And the slope is always your change in y over your change in x. Now what calculus is really interested in is not average rates of change, but it's interested in those tangent lines, instantaneous rates of change. So what we're going to do is we're going to use limits to find tangents. So what I have here from A to B is a secant line. And I'm actually going to start by showing you a little graphic here. So here we go. I've got a curve. I'm going to slide this down so we can see more of it. And can you see that the green line is your secant? And the purple line is the tangent perfectly at 2. And those two slopes are different. But if I take this red dot, and I move it closer, oh, it's moving the, I guess I can't move the red dot. If I take the, what? It's not making me very happy right now. There's a little bit closer. I want to get that red one to catch up. Oh, I know what I can do. No.
Thank you.
What I really, really wanted to do was I wanted to move this red dot here and then draw a new green line like this. And do you see the slope of the green line is closer to the purple one? And if I erase that and move my red dot really close, that's not red, there we go, there's red. And then I drew a secant line between those two, oh my goodness, that would be really, really close. And if I took the limit as they got closer and closer and closer and closer together, would not the secant line get closer and closer to the tangent line? But why can't we just say, well, why don't we just calculate it when it's the same thing? Well, when it's the same thing, to find slope, you need to do change of y over change of x. What's your change of x if it's exactly the same? 0. And you can't divide by 0. So we'd have a problem. And the change of y would be 0 too. So you'd have a 0 over 0 problem, which sounds like a limit problem that we used to solve before. And that's exactly what's going to happen. So if our slope of our line, if we take 2 points, one of them at C and one of them at X, this distance here would be your change in X, and this distance here would be your change in Y. So we could say the slope from A to B is f of x minus f of c over x minus c. But what do we need to have happen here to get the slope of the tangent line? We need x to become really, really close to c. And if we have this equation, and we can evaluate that limit, then we could get the slope of the tangent line. This is idea number 1, formula number 1. Idea number 2, formula number 2. That, or do I have this question first?
Question.
Oh yeah, we have a question first and then formula number 2 comes back. Okay. So we have a parabola. We have a parabola, 3x squared minus 6x plus 1. And at the point 2 comma 1, we want to find out what the slope of the tangent line is. If I draw a tiny little picture off to the side here, I've got some parabola that's going through the point 2 comma 1. Would you agree that that parabola is opening up? So it probably looks something like this. And what we want to find out is if I drew a tangent line that touched only that point, the parabola goes through the point, there we go. What would the slope of that tangent line be? Well, I could get a pretty accurate slope of that tangent line if I took 2 points really close together and did the secant line. But it wouldn't be perfect. If I kept getting closer and closer with my 2 points, then my slope would get closer and closer to what the actual slope of the tangent is. And that's what this limit is doing here. The limit as x goes to c is saying that I keep making x closer and closer and closer to the point c. That's going to get closer and closer to that tangent line. So let's look at the mathematics. Okay, we want to find the slope of the tangent line. It's going to be the limit as x goes to 2 because our c value is at 2. We have to plug in f of x minus f of c over x minus c. Now this part that I'm going to highlight right here, can someone tell me why I didn't have to write this all in and could have done something a lot quicker? What number could I plug in there without having to do any mental math whatsoever? 1. Can you see that if c is 2, f of c would be the y value? They already told you that it happens at 2, 1. So I know that that value is going to be 1. What happens then? The top part, 3x squared minus 6x plus 1 minus 1 over x minus 2. What's the problem with this limit from our limits unit? We're dividing by 0. What did we do when we had those kind of problems? We tried to like factor or simplify to get rid of that problem, right? Can you see that your 1 and your minus 1 will cancel out? And then you have a common factor of 3. And your x minus 2's would cancel out. And what's the limit as x goes to 2 now? 6. So the slope of this tangent line right here apparently is 6. Exactly. Next, the question said, after you found the slope, what is this? Is its actual equation? How do you find the equation of a line? Right? Y equals mx plus b. Do you remember the two things back in grade 10 that you needed to find an equation of a line? One of them was a point. Do we have a point? Absolutely. We know it goes through 2, 1. And the second thing you needed was the slope. You needed the point and the slope. If you have 2 points, you could find the slope. So we know our point and we know our slope. And you have 2 options from grade 10. Equation of line. How many people think of y equals mx plus b first? Okay, then you could use the y equals mx plus b option, where you know the slope, you plug in the point, and you find b, and then you could write your equation y equals mx plus b. How many people remember the point slope formula of the line? The y minus y1 equals mx minus x1, where you just have to plug in your slope for m and your point for x1 and y1. And if you rearrange that equation, you get exactly the same thing. So it's good to know both of those. Here's a picture of what's happening. If we take our parabola and also draw the line, then those two graphs intersect at 2, 1, and we get our equation of our line. So the idea to find that slope of that tangent is that, go back to here, we think about the secant, and we think about dragging this point B closer and closer and closer and closer so that your secant line and your tangent line are basically the same. But you can't physically put them on top of each other and use the same point, because then you would get change of y is 0 and change of x is 0 and run into a problem. But if we think of it as a limit, as x gets close to c, and if that limit is solvable, we'll find our tangent. So let's look at our second example here. We have another parabola going through the point 1, 3. If you want to find the slope of the tangent at that point, and again, this This is f of x, so that's easy to plug in because it's exactly the same as the equation. This part here is f of c, which you really didn't have to write all of that in because I hope you can see that they gave it to you in the question. It's equal to 3. And we're getting really close to the point at 1 comma 3, so x is approaching 1. You have it over x minus 1. And things work out really nice again. The plus 3 and the minus 3 will cancel out. You can factor out a 4x. Your x's go away. And then you just have the limit as x goes to 1 of 4x, which now, as soon as you can get to the point where you plug it in, then you can get your slope. So notice we have to write the limit part all the way along until you can evaluate it, and then you don't have to write the limit anymore. This one says find the equation of the normal. So if our slope of our tangent is 4, the slope of our normal line, which is perpendicular, you remember from grade 10, slopes of perpendicular lines are negative reciprocals, where you take the original slope is 4 over 1, perpendicular slope would be negative 1 over 4. And then, can we find the equation? Well, what are the two things you need to find an equation of a line? You need the slope. Well, here's the equation of the tangent. Does it ask for the equation of the tangent? And yeah. So what are the two things you need? You need the slope and the point. So you have the slope and the point, and you could either use y equals mx plus b, or y minus y1 equals mx minus x1. Either way, you'll find the slope of your tangent line to be y equals 4x minus 1. If you want to find the slope or the equation of your normal line, same thing, you have the same point, but now you have a new slope which is negative 1 over 4. And again, I have both ways here. You can choose which equation you would like to use. They both have their advantages and their disadvantages. The y equals mx plus b usually has more fractions to work with. I actually multiplied to get rid of my fractions temporarily in my other equation. And if we look at a picture of what's happening here, so to recap, method number 1 for finding the slope of a tangent line is you take 2 points on your curve, this green point and this red point. And you slowly make the red point, which is x, get closer and closer to the green point. So we take the limit as x goes to c, because then your slope of your tangent will turn into, your slope of your secant will turn into the slope of your tangent. This is method number 1. Method number 2 looks at the same thing, but instead of taking one point as x and one point as c, you introduce a variable h as the distance between them, the horizontal distance between x and the other point. So if this point is x and this distance is h, does it make sense that this point is x plus h? And instead of making x get close to c, In this idea, we just make h go to 0. If the horizontal distance gets smaller and smaller, then the secant line will get closer and closer to the tangent. So our secant line's change in y is still f of x plus h minus f of x. But now this distance is just h. And if we make the limit as h goes to 0, we get the instantaneous rate of change or the slope of the tangent. And of the two formulas, I would say formula number 2 here is more famous. This is your classic derivative formula. I hate to break it to you, but this whole thing about calculus and derivatives, simplistically, is just finding slopes of tangent lines. And that's what we're going to be working on over the next couple of weeks.